So the question is tickless timer. So what is it? What is it used for? When is the good time to use it? When is it not good to use it? Okay. Yeah. So initially, I was not familiar with this terminology, tickless timer. I was more familiar with dynamic tick timers, but they are same, essentially same. So this gives away how it works. Uh, yeah. So basically, if you see the any micro any embedded system, there is and real-time systems, there is always a need to keep track of the keep track of time, because events or because events may happen asynchronously, or we may trigger events periodically or synchronously. Now, for a simple example is, you want to do a delay of so many milliseconds, let's say 1 second or 100 millisecond delay you want. So this is a very common thing. So let's say you're writing to a peripheral which is going to take some time, or you're reading from a sensor. Let's say you issue a read command, and then by the time the data is available, there may be a small delay, because this sensor may require certain minimum time in order to provide a valid data. For example, you're reading a humidity sensor, you initiate the read, it will take a little time before it can provide a correct result. Sometimes it may require some calibration before it can actually provide the data. So there is always a need for keeping track of delay. So you could program this as a delay. Now that means somebody has to pause this code flow and then restart it after the delay of 100 milliseconds. Now, where does that come from? That comes from the hardware timer or counter. And so the counter, you can program any value in the counter, some 16-bit value. This value is decremented at certain clock rate, at which it is, you can count up, count down also, but yeah, it is changed or updated at a certain clock rate. And when the counter becomes, typically when it becomes 0, if it is counting down, then it generates an interrupt, timer interrupt. Now, this timer interrupt is handled by a timer handler or timeout handler, ISR. Okay, so this is invoked, and this handler is the one which is keeping track of various delays and timeouts that are required in the software. Now, this could be part of the OS or RTOS, or it could be part of the application. It doesn't matter. The point is, so you may have a delay for example, many tasks are there. Let's say you have task A and B, and this is waiting for it's waiting for some mail message in a mailbox or message queue. And you can also specify a timeout value for this. So basically, this is a finite wait. If no message arrives, this timeout will happen. So then for this system call, for this operating system functionality, one timer with this timeout value will be started. So there may be another task which may be using a delay, like we discussed earlier, 100 minutes. So there are at least 2 pending events. One is a timeout event. This is also a timeout event, but basically a delay event. So it is the responsibility of the timer handler, and together with the timer handler, there may be a module in the RTOS which handles the software timers or software events. So there may be a Q which is maintained, and then uh, when the tick matches with the value, so if you say, let's say 1 second, maximum 1 second, so there will be 1000 milliseconds. Now the timer is firing at every 100 milliseconds. So this is invoked at every 100 milliseconds. So 1 second would mean 10 ticks. So basically this is translated into 10 ticks. This may be another 100 ticks, whatever. So each time this timer handler is invoked, the tick is decremented. And when this tick becomes 0, this event fires. So this is how typically software timers work. Now this is part of the operating system. Operating system may also use timers for their own use. For example, using an IO access. So an IO access may have to be timed out, or for any other deadlock breaking. So if no task is getting scheduled for some time, there might be a problem. So a timer might be used to come out of the deadlock by resetting the resources and so on. In certain operating systems, it may be used for time slicing also. If it's not typical in real-time systems, but you might use time slicing for task scheduling. The various internal uses a timer is used. So in a typical system, the tick which is programmed is a hardware event, which eventually calls the handler, and then it eventually handles the software events, including the OS events. So as you can see, every time this tick fires, basically every time the hardware timer expires, it generates an interrupt, which is an overhead. Now, for all you know, as we saw in this, we have 10 ticks to go and 100 ticks to go, and assuming the OS deadlock detection is even longer, it waits for several seconds, then you don't have much to do for every tick other than just decrementing the software counter if you are keeping track of software events. So basically, it does very little thing. There are two issues. One is, of course, interrupts can preempt other tasks. Interrupts preempt other important tasks. So just to keep track of this tick or this software counter, you are preempting an important task. That is one problem. The other problem is power consumption. So what happens is, if you have a very simple system, so let's say it is normally sleeping, and an event triggers the wake up, and then it does some useful work, and then again sleeps. Now imagine this event is application event. So for example, arrival of a packet. Then it's okay. It has to wake up only at that time. But in between, if you are having this tick interrupts, it is unnecessarily waking the CPU, and then it goes back to this after updating the counter or updating the software counter. So basically, what we are saying is that this sleep interval is not long enough. According to the application, it should be several seconds. Let's say the packets arrive sporadically, or for example, it's a beacon device. It just transmits and goes to sleep again till the next interval. So unnecessarily, just because the timer is firing, this is going to wake up. So that means the CPU wakes up. Not only the CPU, all associated memory, etc., all or working, which means it is draining power just to keep track of a tick. So which is why in these kind of conditions where there is long intervals and there between any useful work, this tick, just having the OS tick is an overhead, both from let's say power point of view as well as from performance point of view. So basically, how do you overcome that? That is where tickless programming comes. So let's go back to the example of software event. So you have the message queue timeout interval, which is, let's say, 100 ticks. And then you have deadlock timer timeout, which is 1000 ticks. So if you see the number of ticks, if it is fixed, which is like 100 millisecond, the number of ticks keeps coming before this counter expires or this counter expires. What if we can adjust this to, the next required time interval? For example, you program the, so let's say the tick is not fixed 100 millisecond, but it is programmed based on the earliest event that is there, earliest pending event, which is, let's say, 100 into 100, that is 10 seconds later. And then this one may be even further later. So what you're saying is that you are programming the hardware timer or counter with variable values, variable durations values. Or it could also be that the clock rate of the timer counter can also be scaled dynamically. So then what happens in such cases? The timer fires after whatever 10 seconds. The message queue timeout handler is called, and then the queue is looked up as you have the next event 1000. So we have already expired 100. So there are 9 more such epochs to go. So you will program that time. So the handler is called, and then reprogram the counter with the difference between current time and the next event, pending event. So this delta is what is programmed. I'm assuming that the timer counter has enough bits, 16 bits is sufficient for this purpose. Of course, it's a matter of how you scale the clock and things like that. So there is a trade-off between the range, which is called the dynamic range. This is maximum number of bits that you can use, and the resolution, or what is the smallest time event that you want to keep. So given these two parameters, you can represent large values in a 16-bit counter. So basically what we are saying is that instead of tick happening every fixed 100 milliseconds, it can happen at variable ranges. That means the interrupt is happening only when needed. So that is why it is called tickless programming. If you see this picture, the ticks keep coming, even though you don't have any event changes, except the interval is shrinking. So this is tick. And so in this case, the tick comes exactly when that event expires. So it is basically tickless programming in that sense. But actually there is a tick. That tick happens in variable intervals. And so I would like to call it dynamic tick. And this is more popular terminology, So this is basically the idea. And obviously the benefits are basically less power consumption, because you are waking up only when there is a real event. Now there are complexity to this. This is why it is not very commonly used, because you need to keep track of all the events. Suppose a new event is scheduled, let's say another task is waiting on a semaphore, again with a timed wait. Then you have to insert a new timer value. And that value can be happening before this deadlock. So new timeout entry has to be inserted here. So basically, this is basically like a priority queue with earliest deadline first. Earliest deadline first. Basically, you're sorting on the expiry time of the or number of ticks remaining for this event to expire. So you have to insert it. You have to traverse this list, and there are of course some hash data structures which are also used to reduce this linear list. But the complexity is high. So the disadvantage of dynamic dynamic tick versus fixed tick. If we are to see on the plus side, so this is dynamic fixed. This is simple. And this is complex. And there is overhead. So there is overhead. And here it is having context switch overhead with frequent context switch overhead and frequent CPU wake up. So this is avoided here. So it's only needed context switch and no unnecessary wake up. So basically, that's what I would say. When do you use it? When do you not? So if you are having a complex, so when to use tickless? If you have a simple application which is doing some example of beacon, it is very easy to do dynamic tick because you just have to align to the beacon interval. Basically, for example, in Bluetooth, standard Bluetooth, if you have let's say you have a CPU or a mobile phone is connected to a headset, it's connected to some Bluetooth keyboard, and so on. Now, these devices are very battery powered devices. This is also battery powered, but it's more powerful. So there are two Bluetooth connections. This is a master and this is a slave. This is a master and this is a slave. So what happens is they negotiate the interval, the rate at which they will be transferring data. Headset may be not, it may be a fixed one, but you may also have some other device like, the mobile phone may not be the right example, maybe a tablet. You may have a keyboard and a mouse. So these are hid devices. So you might want to negotiate, these devices negotiate for their own battery saving purposes. They will negotiate an interval with which they will be sleeping and then transmitting. So the duty cycle is negotiated between them. So they periodically transmit. So this is, let us say, the mouse connection, and this is the keyboard connection. So this may, when there is an event, basically you may move the mouse, you may press the mouse. It doesn't mean that event is immediately transmitted to the master. So this is a slot at which they will wait for that slot to happen, transmit, this is the transmit slot, and then after getting the acknowledgement, it will go to sleep. And then any number of presses and movements that you do, mouse movements, mouse events, it will go in the next packet after this interval. It won't go in. Of course, this interval determines your response time for the mouse click and things like that, but they are reasonably small from a user perspective, and they are reasonably large from the power perspective. Similarly, the keyboard events. So they may be happening. So this keyboard event may happen at this slot. And so they are basically interleaved slots. or you could make sure that the master can negotiate such that the keyboard slots are adjacent to the mouse slots. So when the master wakes up, it can finish the mouse event, it can finish the keyboard packets, if any, and then goes back. So this is the master, which is the tablet, let's say. So it can turn off the Bluetooth interface into low power modes. After these two slots, or it listened for these two slots, receive the packets, acknowledge them, and it turns off the radio for this duration. So basically, tickless systems allow you to program variable intervals, and this is one example where it is useful. Now, where it is not useful, very heavy operating system with lot of tasks. You have task one, task n. There is always something happening. So the OS is always running. Very it may be very active with lots of events. So anyway, it is busy. So there is no power save. So typical tick the timer may be good enough here. Is okay. You still have the overhead, but the interrupt overhead. But because if the complexity of maintaining a variable event list is and traversing them for every tick or every event expiry is complex. So if you have lots of timers, timeout events, then the dynamic tick becomes is complex. So it may be avoided. Any thoughts? Anybody has any different points of view? Guru Patil, do you want to comment on this?
Yeah, I have a question. So when you say the events, the so do we use WFE, and that's when it wakes up and then do all the tick stuff?
If so you're asking if so. This is there is the NVIC and then the CPU. Now, if you program the WIC, so when you execute wait for interrupt instruction, okay, basically you are going to, so there are two sleep states. There is a normal sleep or shallow sleep, and there is a deep sleep. And this is controlled by a control register. Um, Depending on what you have programmed, if it is deep sleep, then it is handled by the WIC. So if it is shallow sleep, it is handled by the NVIC. Basically, NVIC will be on in shallow sleep, so it can handle that. In the case of deep sleep, it is handled by the WIC. Essentially, on behalf of, so finally the IRQ will come to the CPU, and then this also interfaces with the power management unit. So if it is a deep sleep state, this power management unit will have to wake up, supply voltage which was turned off, and also restore state, memory state, for example, from NVRAM to, so you will have saved the states. So from NVRAM to SRAM, any state restoration. All this is handled in software, but in consonance with the power management unit. But at the lowest level, the interrupt will be fielded by the WIC when you are in deep sleep state, and by the NVIC if you are in the shallow sleep state.
Yeah, you just mentioned about WFI, but so can we use WFE in this process?
Yes, but that means the interrupt is coming from another CPU rather than from, for example, I think we talked about it in the class. So you have CPU core 1 and CPU core 2.
So WFE is always associated with the another multiple CPU.
Yeah,
Is that
yeah,
right?
that's right.
Oh, okay, okay. Then I know. Yeah. Okay.
Yeah. But from a software perspective, it is so. As I said, this is used for locking and unlocking of shared memory. So when you lock and you don't get that memory, you use a WFE, and only this processor will be turned off if it has nothing else to do. And then when you unlock, this is an event. Unlock is an event triggered by this CPU core. At that time, this basically the lock is available, so it takes up. So it is used in the multi-core, multi-processing.
Oh, now it makes sense
Yeah.
because I have seen these instructions in NRF 840
Mm-hmm.
and probably because it has a different BLE CPU and different ARM. That's why they have been using WFE because I
Okay.
was a little bit confused why they're using WFE. Okay, got
Okay.
it.
Yeah.
This is
So while
excellent.
I'm saying CPU core, it could be any intelligent peripheral,
Okay.
right? Like an intelligent radio baseband. So as far as you're not in a multi-core SoC, this is very easy to understand. But here you may not even know that. So there are some interrupt devices like let's say UART, I square C, timer, and all that, which are all simple. They basically are uh, interrupts. And here, even though it may look like an interrupt, it is coming from an intelligent peripheral. And if they have shared memory, for example, it puts the packet here. Let's say it's a video device. So it puts the RGB values here, and then it can signal an event. So this can wait for this event and then access this shared memory. So typically it goes with multiprocessors with shared memory.
Mm. Okay, that was helpful. Thank you so much.
Okay. Okay. So the next question again from Patil. What is the minimum things uh, to do?
Raghu, I have one question.
Yeah.
At the top.
Who's that?
Yeah, in the tickless scenario, let's say we have already scheduled, let's say if the timer is already scheduled with 100 millisecond, and the
Hmm.
next one is 5 and 10 millisecond, if they come in,
Mhm.
the 100 millisecond will be overwritten with 5 and 10 or 5,
Okay, let
or
me draw the
20
diagram. So you
millisecond
have
will be done.
first event which is after. So we are talking about the 5 millisecond from the time the timer was programmed, right? So this queue is keeping track of remaining ticks or remaining time, right? Now, this was started first. So you have at any given time, you have 5 millisecond remaining time for this event. Let's say this is event one. And what are you saying? There is one more you're saying. Can
So
you
what
just
I'm saying,
repeat?
the timer is already in progress with 100 millisecond tick count.
Mm-hmm.
And then next 10 millisecond came in, and then next 5 millisecond came in.
Mm-hmm.
So 100 is the one which is already in pipeline. I mean, it's already decrementing. The timer is decrementing.
Mm-hmm.
And then next 10 millisecond came in, and then 5 millisecond came in. So what happens to the 100 millisecond one if 10 millisecond comes in?
Yeah. So basically, what it tells is that let's say it has decremented to say 95 or 98. 2 ticks have expired, right? I'm assuming every millisecond you are getting a tick. Okay.
Okay.
Now, so 100 became 98 now. At that time, 10 millisecond timer is coming, which means basically from current time. So this is T, this is T1. At T, it was 100. These were not there at that time. Okay,
Mhm.
only 100 was there. Then
Okay.
2 ticks have passed, so the remaining time is 98. At that time, you are getting a 5 millisecond timer. So basically, this is remaining from currently. It has 5 more ticks required, and this has 98 more ticks required. So obviously, this is the earliest event, right? This will have to fire first. So the queue will become like this, 5 followed by 98. Okay, this is at T1. Then some more ticks happen. Let's say you have 2 more ticks happen. So this will become 3 and this will become 95, right? Sorry, 96, right? Then you get another 10 millisecond timer coming. And this 10 millisecond timer is more than 3. The remaining time is 10 millisecond because, or 10 ticks, because it is from current time. So the insertion will be like this. Okay. And then when the next tick, so the tick happens, another delta happens. So let's say three ticks expire at T3. So what you're saying is that you are programming for 5. You are not getting the tick. This is in fixed tick context, right? So you are in the dynamic tick context. You are programmed it for 100 ticks. You are not yet decremented this. It is still not firing, etc. It will fire only after 100 milliseconds. Okay, so your timer is still running. At the counter is running. Maybe it has decremented by 2, but no ticks have happened. Okay, a new timer value which is less than the current value is happening. Then the timer will be programmed for this, not this. Okay, you understand that there is one hardware timer. It is going to generate the ticks. The tick value will be reprogrammed from 100 or remaining time of 98 to 5. The 98 will be turned off basically, because this is all you are interested in is the immediate event that will be expiring. Let us see at that time when it expires, it will track this and then reprogram it. Let's say when this expires, it becomes 93, right? This is 98 minus 5. So 93 ticks are remaining. So it will reprogram the timer counter with 93. Then one more timer came 10 millisecond. So it will be the 93 will be stopped and a 10 millisecond timeout will be programmed, and this will be adjusted to 83. That's the way it works. So what I described was for fixed tick programming, and the same thing for a dynamic tick programming will be the timer. Maybe I should draw that again. So you initially had a 100 millisecond tick or event 1. Okay, so this is the event queue. This is the time and the timer, hardware timer or counter, sorry, timer hardware value. Okay, if you keep track of this, at time T0, it is programmed for 100 millisecond tick, and you have one event available. At T1, a new event comes, which is a 5 millisecond event. So what happens? This will be programmed 5 milliseconds from now. So the hardware timer will be programmed for 5 milliseconds. And the queue will be like this. The event list will be like this. And so 100 becomes basically, sorry, T0 and T1, let us say 2 ticks expired. Okay. So from here it is 5 millisecond. From here it is 98 millisecond. But it won't be adjusted at this time. When you're inserting, you can adjust it. That's up to the software. Or it may just keep that value there. Then what happens is the next timeout will happen after 5 milliseconds. So this event has expired. So this is the next available event. So it will be the timer counter will be programmed with the remaining time, whatever 98 minus 5 equal to 93. So the timer counter value is varying depending on the remaining time of the head of the queue. So it is basically, if you think of this as a queue sorted on increasing remaining time, the timer counter will be programmed with the head of the queue value. That's the way it is. And then all other things will be correspondingly reduced. So basically what you will be storing is the not the absolute value, but the remaining time, 98 minus 5 and so on. So basically that way it is simpler to do in software without going through the list and updating everything. So, but your question is pertaining to the hardware timer. The value programmed will be the head of the queue, remaining time of the head of the queue. So two instances where this is reprogrammed. One is when it expires. Other is when a new timer is inserted. So you may have to reprogram it. But if the new timer is further in the future than the head of the queue, you don't have to reprogram the countdown. But when it expires, the next in the queue, the remaining time of that is programmed. Did it clarify?
Yeah. I'm still thinking about the difference with fixed one actually.
No, the fixed one, the timer value is fixed. The timer counter value is like 10 millisecond or whatever you program it. Here it is variable. That's the whole essence of the dynamic timer. So you can think of rest of the things as detail. Okay, think of this timer counter value. It is variable. Whenever a new event is scheduled, that remaining time is programmed in the hardware counter. That is for the head of the queue. But you need to keep track of all pending events, so there is a queue. So this value is, so that means the timer will fire only after this count is expired. Okay.
Hey Raghu, I have a question. Yeah, so here, yeah, I understood everything, but my question is, how the processor will know that there is an event that has occurred and it needs 5 millisecond of timer because it's supposedly sleeping, right?
No.
Or throughout the.
If it is sleeping, it need not know. There is no new event happening, right? So there are two scenarios. When you do one thing like maybe transmit on Bluetooth and then sleep for whatever X intervals, and then repeat. In this case, it is sleeping. Yes, there is no event which is happening here except the Bluetooth event which will happen whenever that event happens. It will wake up and do that. In that case, there is no. So basically, what you are saying is there is basically, if the tick itself, the timer tick, which is keeping track of the real-time clock or something, will be coinciding with this packet array. See, packet may or may not come, but you have to. So if you see so you have the CPU, you have the Bluetooth, Mac, and the radio. Okay. Now, when it says, this beacon case, if you're doing a receive, what happens? You don't know whether a packet will come or not unless you wake up, right?
Yeah.
So you have to wake up. So that is where you will program that for whatever the negotiated interval of the beacon interval or whatever the low power
Right.
interval. So you will program the timer tick to that interval value. Okay. Then the timer fires. The CPU wakes up. Then it will restore the MAC and the RF, and the packet may or may not come in that slot. If a packet comes, it will do the packet processing and then again reprogram the timer to the next slot. That is basically remaining time for the next slot, and then goes to sleep. This is one scenario. Here, what you are programming is depending on. So, for example, you are saying reprogramming the timer. Now, depending on the type of packet, you might have spent more time processing that packet. So, the remaining time may be variable depending on the complexity of the packet processing. So, you will program a slightly different value, not a constant value there.
Right.
Okay. So,
but
the next event is determined by the protocol.
I'm sorry. Yeah. So this, yeah, exactly. So this event is pre-known, like it's defined by protocol that advertisement interval or some kind of. But what about the random events?
What about the
random events?
Yeah. So what are they? You have to define them, right? So
yeah,
depending on your system, like I described the mouse and things like that on the Bluetooth, but you could have internal, let's say it's a mode device. Okay, so the mode has the CPU, the Bluetooth interface, and maybe a sensor. Depending on what this sensor is, what type of sensor it is, it could be an industrial valve or something. So it may generate interrupts here. Now, these are not periodic interrupts. These are sporadic interrupts. Or you may be polling for data, polling for sensor data. Polling is obviously, spinning the CPU. So you could substitute polling with a timer value, which say you wake up and then check for data, sensor data. If data, do processing, and then do transmit on Bluetooth. This is their application logic. So what you're saying, there are two ways. If the sensor is capable of generating an interrupt whenever the data is available, you may want to just use the interrupt. There is no timer involved there. This is a sporadic event, asynchronously. There may be a situation where you may have to, periodically poll something. For example, many motor drives, instead of sensor, think of it as a motor. Motor is driven by some PWM signals. Okay, these signals are basically generated from a timer, hardware timer, based on whatever the pulse width is. So you would probably have a pulse interval and the active interval in there. Okay, so the GPIO line is on for this long and then off for this long. So you are basically using a timer in any PWM situation, but not as a generic timer, but for a special purpose. So these are all periodic events, but that has nothing to do with the timer tick. If you're doing it in software, like polling through timeout value, then as the timer comes, the ticks come into picture.
Oh, I see. So here interrupt is the event
Yes.
that we're talking. Okay, got it.
Yeah.
Okay. Sporadic interrupt, it's itself event. Because the
Yeah.
event and interrupt sometimes it's referred little bit differently, but it depends on the context of discussion. But okay, now I understand. Thank you.
Okay.
Raghu, I have one question. Can you go back to slide number 15? So here, right? So we are not taking any action for every millisecond tick. So we'll
Right.
take action only when the interrupt is fired after the lowest thing is done.
Correct. Correct.
And rest of the data structures, whatever we have queue, it is a pure software thing. So we have to maintain it, right? The 98
Yes.
milliseconds and all of that.
Yes.
Okay.
Correct. Yeah.
And
yeah, go ahead.
yeah, go ahead. That's another question. So you
Yeah.
can just
So
complete it.
normally what you said is correct. Whenever the earliest deadline event expires, then you will go to the next earliest event. But in between, if you're starting a new event, you're enqueuing new event, it may happen that may become the earliest event. So you may have to reprogram the timer.
Got it. And here, for the simplicity's sake, we have taken 1 millisecond as the clock duty cycle, right? Mainly, my question was, what happens if we get another request in between ticks? Meaning, like,
you may get a request. The question is, what is the expiry time? So first of all, we are not using a fixed tick like 1 millisecond. That is in the normal ticked mode of timer. In the tickless case, you are programming the hardware for multiple ticks. It could be 5, it could be 100, whatever it is. So there is a slight confusion there. So it is not like every 1 second, 1 millisecond, there will be a tick. There is no tick. The tick is variable. That is why it is dynamic tick. It may happen after 5 milliseconds. It may happen after 100 milliseconds. We don't know. Okay. In the dynamic tick. Now, in either case, whether it is dynamic or fixed tick, a new event can come, no problem. But you cannot have an event, at least in the fixed tick case, if your tick rate is 1 millisecond or 100 millisecond or 10 millisecond. You cannot have an event that will expire in less than the 10 millisecond because the resolution is once in 10 millisecond, right?
Yeah.
You cannot have an event. You can have an event coming between ticks, not a problem. But its expiration will be a multiple of ticks. So it will be after k ticks from now. So you might say, okay, you can split here and say, okay, here is the last tick that happened. There is a 10 millisecond gap. The next tick will happen. A new timer event happened, or rather new request came. Okay, should I count that? And let's say next request came with k ticks. Okay, after k ticks, it should expire. Should I reckon from this or this? Okay, if that is the case, it probably is subjective. You could reckon from the next event rather than from the past event. Okay, so it may be k plus 1 or k minus 1 depending on how you reckon it, but that is a small detail. In a fixed tick case, this may happen. Okay, in a dynamic case, it doesn't matter. Yes, if the next, so here the dynamic case, if you had the last tick event and this is after the next tick is after 100, so this is 100 millisecond, and the new request is saying say 10 millisecond. Obviously you cannot wait till here, so you have to start right here. Basically what you're saying, so let's say you expired 20 milliseconds so far when this came. So the remaining, so this whole thing is 100, the remaining time is 80. If this request is 10, between 10 and 80, you have to choose 10. So what you will do, you will reprogram the timer so that at this point in time, so 20 milliseconds have expired. In the next tick will adjust to the 30 millisecond. Okay. So this is the next tick. And then the future, that whatever remaining 80 millisecond may be in the future, that whatever originally was 100 is pending here. So your next tick is adjusted for the smaller of this remaining value and the new value.
Got it. Okay. And whatever we are programming here, 5 milliseconds, it's basically a counter, right? It just for understanding sake, we are using milliseconds, but
exactly. So basically, if you have programmed any timer, it is basically a counter, which has a 16-bit or 32-bit counter, and the counter is decremented
based on its clock, right?
Clock, yeah. So you can program the clock may be in so many hertz. Maybe it is 100 hertz or whatever. Depending on whatever the hertz that you program, the clock counter will decrement. So you can think of it that way. And normally you will have a scaling, pre-scaling, etc. So that this clock is supplied by the hardware derived from some other system clock, and you play with this scaler so that you get the frequency that you want.
Got it. Thanks.